Okay, so this question is about maintaining a safe braking distance when driving. Consider a car driving on a straight road at 45 miles per hour. The driver brakes and decelerates at 3 meters per second squared until the car comes to rest. Consider a second car driving behind the first at the same speed. When the first car brakes, the driver of the second car takes 1.2 seconds to react, which is actually quite a quick reaction time in the context of things. It can be a lot bigger than that. Before braking with the same deceleration of 3 meters per second. Okay, so they've got the same deceleration, so that's not going to be different. It's just this time between them that's important. So 1 mile is 1.6 kilometers, show that 45 miles per hour is 20 meters per second. So the first thing I'm going to do is I'm going to convert miles per hour into kilometers per hour by multiplying by 1.6. And then I'm going to turn the kilometers per hour into meters per hour by multiplying by 1,000. And then what I'm going to do is, well, if there's 72,000 meters in an hour, we need to divide that by 60 and then by 60 again to turn that into meters per second. So that's what I'm going to do here, giving us 20 meters per second. All right, so now we want to draw a velocity time graph for each car. So we're going to need to label each and add scales to the axes, and then once we've got the graph, we want to calculate the minimum distance between the two cars. So the velocity axis is pretty easy because we know they both start at 20 meters per second, so that's easy enough to label. The time axis, we're actually going to need to do some calculations. So I'm going to use the average acceleration equation here. When I'm using the symbol V, that means it's final velocity. The symbol U means initial velocity. The final velocity is 0 because they're coming to rest, and the acceleration is -3 because we're told there is a deceleration of 3. So that allows us to calculate the time for car 1 to stop, 6.7, and if we add 1.2, that gives us the time car 2 stops, 7.9. So now we can put our scale in on our time axis. I'm going to go up in 2s to make that fit. The first car is pretty straightforward, starts at 20, ends at 0. That happens in 6.7 seconds, and the deceleration is constant, so it's a straight line. The second one is pretty straightforward too. It keeps going at 20 for 1.2 seconds, then has the same deceleration and therefore the same gradient, stopping in 7.9 seconds. So now we can get the distance between the two cars, which I'm going to use the average velocity. So the distance is going to come from the 1.2 seconds. The second car is still traveling at 20 meters per second. That's going to be the distance we need. So we can rearrange that, do average velocity, which is 20, because it's 20 during that whole period, times by 1.2 gives us 24 meters. Okay, so continuing with the theme of braking distance, there are actually things on motorways to help them. They're called these chevrons, these arrows that you can see on the road. And they're there to help drivers keep a safe distance apart, or anyone who's ever been on a road, unfortunately, will note that a lot of drivers ignore these, which is presumably why we end up with lots of crashes on them, or at least one of the reasons. Okay. So the chevrons are 30 meters apart. The driver takes 1.2 seconds to react, same as before, same deceleration as before, 3 meters per second squared. At what speed would using the chevrons no longer provide a safe braking distance? So essentially it's asking us what speed would they be traveling at that it covers that 30 meters in the 1.2 seconds. Okay, so what we're going to do is do 30 divided by 1.2, that's 25 meters per second. So actually not that much bigger than what we were dealing with in the previous question. So the previous question, you're actually quite close to crashing into each other. An alternative way to ensure a safe braking distance is to time 2 seconds between the car in front and then the second car. So you say you always know that you're 2 seconds behind the car in front. And if anyone of you watch Formula 1, this is actually how they measure the distance between cars. They don't do it with distance, they actually measure the time between cars. So how does this work? Well, if a driver's reaction time is 1.2 seconds, if they are 2 seconds behind the car, they're always going to be able to stop, provided that they can match the other car's deceleration. or how to do bigger than that, that would work. And that would actually allow you 0.8 seconds of spare time to allow for the fact that maybe you're a bit tired and your reaction time is a bit longer than usual. Okay, so slightly different question at the end. We're going to look at a question on an elevator. So these are classic mechanics type problems to see who can really think about what's going on. So an elevator going up accelerates and rests for a few moments and then goes at constant velocity. The person in the elevator experiences a sensation of being heavier for a few moments, during which the elevator is initially accelerating. Explain why the person feels heavier. So the first thing to say is the person does not get heavier. Their weight force does not change, or their mass doesn't change. But people don't measure how heavy they are from their weight force. People measure how heavy they are from the reaction force on the floor. So if the normal force from the floor gets bigger, that person's going to think they're heavier. That's going to be the key. So let's draw a diagram of the setup during the acceleration phase. So if the lift is accelerating, it stands to reason that the person inside it must be accelerating too, because they're not falling through the floor or anything. And if the person is accelerating upwards, there must be a resultant force upwards. And that must mean the normal force from the floor, which I'm representing with the symbol R, because it's often called a reaction force, must be bigger than their weight force. So if the normal force is bigger than their weight force, the resultant force is then upwards, and therefore they accelerate upwards. So that's all fine. And because people measure how heavy they are from this normal force, that must mean that they feel heavier during this time.